They laughed at Japan. They said the country had lost its mind by sinking massive metal structures into the ocean and calling it a solution to its energy crisis.
Japan's government is pushing nuclear energy once again as it tries to end electricity shortages and improve efficiency.
But in 2025, the project branded as reckless has become unstoppable. And the way Japan pulled this off is very hard to believe. What few remember is that this dream began not with triumph, but with a nightmare in 2011. The energy nightmare. On the morning of March 11, 2011, life in northeastern Japan changed forever. A massive earthquake, one of the strongest ever recorded at 9.0 in magnitude, struck off the coast. The violent shaking was only the beginning. Within minutes, a wall of water more than 40 feet high surged toward land. Entire towns were swallowed, cars and homes were tossed aside like toys, and thousands of people fled with only seconds to spare. At the Fukushima Daiichi nuclear power plant, the situation quickly spiraled into a nightmare. The tsunami waves crashed over the plant's seawall and flooded the emergency generators. These generators were the last line of defense meant to keep the reactors cool in case of a failure. Without them, the nuclear cores overheated. Explosions ripped through several reactor buildings, sending huge clouds of radioactive material into the air. The Japanese government ordered mass evacuations. Families were forced to leave everything behind with little warning. Over 150,000 people were displaced. Many never returned because the contamination was too severe. To this day, several towns remain uninhabitable, frozen in time as reminders of the disaster. Schools, farms, and neighborhoods were abandoned, and residents lost their homes, their communities, and their sense of security. Before Fukushima, Japan had relied heavily on nuclear energy. Nearly one-third of the country's electricity came from nuclear power plants. After the explosions, that confidence was shattered. Within months, reactors across the nation were shut down. Japan went from a country with one of the most ambitious nuclear programs in the world to one struggling to fill a sudden and massive energy gap. With nuclear power essentially gone, Japan had little choice but to turn to imported fossil fuels. Tankers carrying liquefied natural gas, mostly from Australia and the Middle East, became the lifeline that kept the lights on. This dependence created a new vulnerability. Japan was now at the mercy of global fuel prices and supply chains, leaving its economy exposed to risks it could not control. Ordinary citizens felt the consequences in their daily lives. Rolling blackouts became common in some regions. Electricity bills rose sharply, putting strain on families and businesses already recovering from the earthquake and tsunami. Fear of future shortages spread across the country. People worried whether Japan could ever achieve energy stability again. The images from that time were heartbreaking. Families who had lived for generations on ancestral lands had to abandon them overnight. Farmers were forced to slaughter animals they could no longer feed or sell because of radioactive contamination. Children went to school wearing radiation monitors, and parents feared that their kids would never grow up in a safe environment. The Fukushima disaster left a scar that was not only physical, but also emotional and cultural. Confidence in the government's ability to keep people safe was badly damaged. In the years after Fukushima, Japanese engineers and policymakers faced a problem that seemed almost impossible to solve. Nuclear energy had collapsed as a trusted option. Fossil fuel imports were draining the economy, and renewable energy sources like solar and wind were struggling to provide consistent power at the scale Japan needed. Out of this desperation came an idea so bold that it made the world laugh at Japan. Japan would turn to the one resource it had in abundance, the powerful ocean currents running along its coast. The audacious plan to harness the ocean. The Kuroshio Current became the center of this vision. Known as one of the strongest ocean currents in the world, it flows northward past Japan's Pacific coast like a massive underwater river. Unlike wind or sunlight, which fluctuate depending on weather, ocean currents move day and night, season after season, with remarkable consistency. This stability is a dream for energy planners because it means the electricity supply would be steady and predictable rather than intermittent. If Japan could capture even a fraction of the Kuroshio Current, it could secure a new and reliable energy source for decades. The idea was straightforward on paper, but radical in practice. Japan would sink massive turbines into this current and let the force of moving water turn giant blades to generate electricity. Instead of filling land with solar panels or covering hillsides with wind towers, the country would build its power stations under the sea. These turbines would not be seen from the shore and would not take up precious space on land, making the plan politically appealing in a crowded island nation. Early studies suggested that the Kuroshio current contained staggering potential. Analysts estimated that if even part of the current could be harnessed, it could provide up to 200 gigawatts of electricity. That number was more than Japan's entire national demand, meaning the current alone could theoretically power the whole country and still have energy to spare. For politicians, this vision became more than a technical plan. It was a symbol of recovery after national tragedy. Newspapers framed the concept as a chance for Japan to lead the world in a new kind of renewable power. The ambition was breathtaking, but it also sounded unbelievable to many. Before the first turbines were ever lowered into the sea, critics were already lining up. Mockery, blackouts, and the 2018 Hokkaido tragedy. From the start, Japan's plan to sink giant turbines into the ocean was treated as a national joke. Commentators laughed that the country had lost its mind and was wasting money on fantasy projects at sea. Business columnists sneered that Japan was chasing a dream fit for cartoons, while the rest of the world built practical solutions like wind farms and solar grids. International critics were even harsher, declaring, "Japan wants to power itself with invisible machines in the deep ocean, but it cannot even keep the lights on during a storm." Critics immediately turned to the 2018 blackout. In September that year, before dawn, a powerful earthquake struck Hokkaido. Measuring 6.7 in magnitude, it shook the island hard enough to topple homes, while landslides buried entire communities. But the true disaster came when the Tomato Atsuma thermal power plant, which supplied almost half of Hokkaido's electricity, was knocked offline. In an instant, the entire grid collapsed. All of Hokkaido went dark. More than 5 million residents lost power. Trains stopped on their tracks. Traffic lights went out, throwing intersections into chaos and creating massive gridlocks. Families were left in freezing apartments with no light, no heat, and no way to keep food from spoiling. Hospitals switched to emergency generators, but some ran dangerously low on fuel. Doctors were forced to work by flashlight, fighting to keep patients alive as machines began shutting down around them. The blackout took lives too. One of the most heartbreaking cases was a young girl in a hospital who relied on a ventilator to breathe. When the power went out, her life support system failed. The backup generator could not keep her machine running long enough. She died in the dark, and her parents could only watch helplessly as doctors tried to keep her alive with equipment that no longer worked. On the roads, another tragedy struck. A middle-aged truck driver was caught in one of the massive traffic jams created when traffic lights failed across the island. Cars stretched for miles, locked in lines with no escape. The driver was forced to sit for hours in the sweltering cab, with no way to move and no immediate access to medical help. He suffered a fatal heart attack while trapped in the jam, and by the time rescuers finally reached him, it was too late. His death shocked the nation and stood alongside the ventilator case as proof that when Japan's power failed, it did not just inconvenience people, it killed. The tidal turbine project became an easy target in the aftermath. Politicians and commentators pointed straight to Hokkaido. They said Japan had no business pouring billions into sinking machines in the ocean when people were dying on highways and in hospitals because the national grid was so fragile. Online forums were even crueler, with commenters saying the only thing Japan's ocean project was powering was the laughter of the world. Yet even with the sting of that humiliation, Japan's engineers refused to back down. Away from the headlines, they began preparing their first real step into the ocean. First steps: sinking the pilot turbine. In 2021, Japan finally moved from theory to practice. The country launched its first real experiment with ocean current power by installing a prototype turbine known as the AR-500. This was a pilot device, built to test the technology on a limited scale before attempting larger deployments. The AR-500 could generate 500 kilowatts of electricity, enough to supply a few hundred homes, but far below what Japan needed nationwide. It was never meant to solve the crisis on its own. Instead, it was a learning tool placed in the Nauru Strait to prepare engineers for the much bigger goal, tapping into the Kuroshio current, which held the potential to generate as much as 200 gigawatts of power. While modest in size, the AR-500 represented a critical first step toward that ambition. The team began by placing the turbine in the Nauru Strait, a narrow body of water in Japan where ocean currents are strong and steady. Choosing this location was strategic. The strait offered powerful enough water flow to turn the blades consistently, but was also close to shore, which made it easier to connect the device to monitoring equipment and carry out repairs. The AR-500 worked on the same principle as a wind turbine, but instead of blades turning in the air, the blades were turned by the force of moving seawater. Ocean water is about 800 times denser than air, so even a relatively slow current carries a tremendous amount of energy. This density allows water-driven turbines to generate more power with smaller blades compared to wind turbines. However, it also means the stress on the equipment is far greater, which is why the pilot was essential to test durability. One of the biggest engineering challenges was anchoring the device. On land, a wind turbine can be bolted to a solid foundation. In the ocean, the seabed is uneven, shifting, and constantly subjected to enormous forces from tides and storms. Engineers had to design a mooring system strong enough to hold a 300-ton structure steady under extreme pressure. They adapted techniques from offshore oil rigs, which have decades of experience in deep-water anchoring. Thick steel cables were driven into the seabed, while floating platforms kept the turbine suspended in the strongest part of the current. Another challenge was corrosion. Saltwater is one of the most destructive environments for machinery. Metals rust quickly, and moving parts can seize up if not protected. To fight this, the turbine blades and rotors were coated with special anti-corrosion layers and made from composite materials designed to resist both rust and the growth of marine organisms. Without these measures, the blades could quickly become encrusted with barnacles and algae, a problem known as biofouling, which reduces efficiency and can damage equipment. The AR-500 was also connected to a network of sensors. These sensors measured water flow, blade rotation speed, pressure on the anchors, and vibration levels inside the machinery. All of this data was sent to monitoring stations on shore. This constant feedback was critical because the engineers wanted to know not only whether the turbine produced power, but also how it survived weeks and months of non-stop operation in a harsh environment. Once the turbine was installed, it began generating power successfully. The electricity output was limited, enough for only a few hundred homes, but that was never the point. The pilot was designed to answer key questions. Could the structure survive heavy storms? Could the blades turn continuously without breaking? Could maintenance crews access the machine safely? And most importantly, could the system provide stable, predictable electricity without major interruptions? The results were promising. The AR-500 demonstrated that ocean turbines could generate reliable power under real-world conditions. It also gave engineers valuable lessons. They learned how the anchors shifted during storms, how the cables wore down over time, and how often the turbine would need maintenance. Each problem revealed by the pilot became an opportunity to strengthen the design for the larger turbines that would follow. But moving from a small pilot to full-scale turbines was a different challenge altogether. The moment Japan tried to scale up, the problems multiplied, and the wave of mockery came crashing back. Setbacks and intensified mockery. The first issue was cost overruns. Installing turbines in the open ocean was far more expensive than engineers had projected. Every stage, from transporting heavy equipment to hiring specialized ships and divers, cost millions. Building a turbine that could survive constant exposure to seawater required advanced materials and coatings that drove prices even higher. Then came wear and tear. The pilot had already shown how corrosive and punishing the sea could be, but larger turbines suffered in ways that calculations had not fully predicted. The anchors shifted more than expected during storms, which meant expensive repairs. Cables that carried power back to shore began showing damage earlier than planned. Even the turbine blades, designed with anti-corrosion layers, developed cracks from the enormous pressure of fast-moving currents. The most visible failures came when early larger prototypes were placed in rougher waters. Some turbines experienced mechanical faults within months. Bearings wore out, gearboxes jammed. In one case, a machine broke free of its moorings and had to be salvaged at enormous cost. Crews had to mount rescue operations with cranes and barges, spending millions just to haul damaged equipment back to shore. Each of these setbacks was amplified by critics. The press was merciless. Headlines mocked the project as a sinkhole for taxpayer money. Commentators compared the ocean turbines to submarines that do nothing but eat cash. Business analysts asked why Japan was sinking structures when offshore wind is cheaper and proven. The laughter that had followed the plan years earlier now returned even louder, armed with fresh evidence of failure. Other countries' progress only made the humiliation sharper. Europe, especially the United Kingdom and Denmark, was seeing enormous growth in offshore wind farms. The technology was proven, the costs were falling, and turbines were delivering electricity reliably to millions of homes. Against this backdrop, Japan's experiment looked increasingly foolish. Instead of joining the global success story, it appeared to be stuck in its own expensive detour. At home, opposition grew louder. Japan's budget was already stretched by the cost of rebuilding from earthquakes, tsunamis, and aging infrastructure. Politicians and public figures began to argue that the country could not afford to waste money on projects they called dead on arrival. They demanded that funds be diverted to repairing the fragile national grid, rebuilding hospitals, and fixing crumbling roads. For many citizens, the memory of the 2018 blackout was still raw. They asked why the government was experimenting with the ocean while people had died because of failures on land. Inside the engineering teams, the atmosphere was suffocating. The scientists and technicians knew the problems were not impossible to solve, but they needed time, data, and funding. Instead, they faced daily headlines questioning their competence and politicians hinting at shutting down the program. Each failure was not seen as part of the learning process, but as proof the whole concept was doomed. For a while, it seemed the critics might be right. The setbacks piled up, the ridicule intensified, and the dream of ocean power looked like it might collapse under its own weight. And yet, against all odds, a breakthrough came that changed everything. The first breakthrough. By early 2025, after years of frustration, Japan finally made the leap from small-scale experiments to something that truly mattered. The nation installed its first megawatt-scale tidal turbine, known as the AR-1100, in the Nauru Strait. Unlike the earlier pilot, which had been little more than a proof of concept, this machine was designed to show the world that tidal energy could work at a national level. The AR-1100 earned its name because of its capacity, 1.1 megawatts. A single megawatt is enough to supply hundreds of homes with electricity, and this turbine promised steady, uninterrupted output. Unlike solar panels, which stop generating at night, or wind farms, which can go idle on calm days, tidal energy is driven by ocean currents that never stop moving. That stability meant the AR-1100 could deliver electricity to the grid every hour of every day, providing a kind of consistency Japan had been desperate for since Fukushima. The engineering behind the AR-1100 was remarkable. The turbine's rotors stretched wide like an underwater windmill, designed to capture the dense flow of seawater. Because water is so much heavier than air, the blades could rotate slowly and still generate large amounts of power. This reduced wear compared to high-speed turbines and made the system more durable. The entire structure weighed hundreds of tons, and its installation required specialized ships, cranes, and divers working together with precision. Anchoring it was a challenge in itself. The currents in the Nauru Strait are powerful, and storms often sweep across the Pacific with devastating force. Engineers used mooring lines similar to those developed for offshore oil rigs, embedding massive anchors into the seabed to keep the structure steady. Once the turbine was in place, the next test was connecting it to the grid. A heavy-duty submarine power cable was laid across the seafloor, linking the turbine directly to Japan's national electricity system. This connection was historic. For the first time, power generated from an underwater current flowed into homes, businesses, and hospitals across Japan. What had once been dismissed as science fiction became visible in real numbers on the grid. When the system went live in February 2025, engineers on shore watched as the meters ticked upward. The AR-1100 was generating at full capacity, delivering steady electricity day and night. For the teams who had endured years of ridicule, it felt like vindication. But the true revolution came not just from the installation itself, it came from what happened next. From ridicule to revolution and the future of an ocean-powered Japan. The turning point came in mid-2025 when Japan's Ministry of Economy, Trade and Industry, METI, formally certified the AR-1100 as a grid-worthy renewable source. The media, which had once ridiculed the project, flipped almost overnight. Headlines that had mocked Japan for chasing fantasies in the sea now ran stories about Japan's ocean revolution. Commentators who had laughed at the idea of giant turbines underwater began comparing the breakthrough to Japan's proudest engineering achievements, like the Shinkansen bullet train. Public opinion also shifted. For years, ordinary citizens had grumbled about money being wasted offshore while blackouts struck at home. But with government certification and news coverage celebrating the achievement, many began to feel pride instead of doubt. Investors noticed the shift as well. Venture capital firms that had avoided the project began pouring money into marine renewable companies. Large corporations signed partnership agreements to accelerate research and production. Shipbuilders saw opportunities to expand into turbine transport. Material science companies invested in new anti-corrosion technologies. The success of one turbine had unlocked a wave of economic activity across multiple industries. The technological benefits spread beyond energy. The engineering solutions developed for the turbines began influencing other fields. Advances in underwater robotics, used to inspect and maintain the turbines, improved Japan's capabilities in marine exploration and deep-sea research. New alloys and coatings designed to resist saltwater corrosion found applications in shipping, defense, and construction. The future possibilities are enormous. If Japan expands beyond a single turbine and builds full arrays, entire regions could be powered by ocean currents alone. The implications for agriculture are clear. Reliable, cheap electricity can drive large-scale desalination plants, giving farmers a new source of fresh water and increasing food security. In healthcare, stable power would protect hospitals, ensuring life support systems stay running, even during crises. For climate policy, the breakthrough could be decisive. Japan has long been criticized for its heavy dependence on imported liquefied natural gas and coal. With tidal energy scaled up, the country could slash those imports, cut carbon emissions, and move closer to carbon neutrality. That would not only protect the environment, but also shield the economy from fluctuations in global fuel prices. Economically, Japan could become the Denmark of tidal energy, exporting not just turbines, but also the expertise to install and maintain them. This would strengthen its global standing and provide leverage in international negotiations, particularly with developing nations eager to adopt clean power. Countries like Chile, with strong coastal currents, or island nations vulnerable to climate change, could adopt Japanese technology. Each installation abroad would reinforce Japan's role as a global leader. Most importantly, scaling tidal energy could give Japan true resilience. Future earthquakes or typhoons would no longer paralyze the grid the way they once did. A diversified energy system, with currents providing a constant baseload, would mean blackouts are less likely to spiral into national crises. The tragedies of Fukushima and Hokkaido would not be forgotten, but they would not be repeated in the same way. Now that Japan has proven turbines can survive, operate, and feed the grid, the path is clear. The next frontier is moving from controlled straits into the Kuroshio itself, where the true scale of this revolution will be unleashed. And once Japan masters the Kuroshio, it will not stop at its own shores. The same technology could be exported worldwide, bringing clean and constant energy to nations with powerful currents of their own, from Southeast Asia to South America. What was once laughed at as a doomed fantasy has become Japan's unstoppable path forward, proof that persistence, tragedy, and vision can rewrite history.